As students here at Georgia Tech, we are oftentimes interested in the quality of our professors and the classes that they teach before we register for their classes. However, there are two very different evaluations that can be given to every professor: the student's opinions of the class and the GPA distribution of that class. Obviously, the ideal situation would be a professor who is held very highly by his or her students and also has a good GPA distribution. However, this is oftentimes not the case. In our project, we hope to find a correlation between these professors' ratings by students on ratemyprofessor.com and the professors' grade distribution reports on Course Critique. We will attempt to find correlations between the two and be able to model these trends. We also hope to allow the user to input specific characteristics of a professor in case there is not data about this professor on ratemyprofessor.com, and be able to predict the average GPA and describe if taking that class with that professor is a good idea. I know code review is super boring, so I'll try to talk about this as quickly as I can. So my first program, findprofs.py, utilizes Python Selenium package, and it automates my search of ratemyprofessors.com. And I also use Phantom.js to make sure that this process is headless. The code goes to this website right here. I have it opened in Chrome. And then it simulates clicks on all of these individual letters from A to all the way to Z, as we can see here. And then it parses the HTML data for these various professors, and that's what everything in this for loop does right here. And then eventually I will spit it out into a text file, which is called profs.txt, and I'll open that for y'all right now. And then here we can see it gives the HTML data for all the professors. We have the name here, and then we have what's most important, this ID number, which will come in handy really soon. So this here is the heavy program that does most of the actual scraping from ratemyprofessors.com. From the text file that we had just generated with the HTML data for all the professors, I used regular expressions and found the ID number, which was this important number right here, for all of the professors. I then used Python's requests and beautiful soup packages to get the site's HTML data, and that's what this function right here does. It finds the overall rating, the number of ratings, and the percentage of students who would take this professor again, the level of difficulty, and all of the top tags for the professor. Here's a sample page of everything that I'm scraping. So it has the overall rating, it has the professor's name, the percentage would take again, and the level of difficulty, and all of these top tags right here. And also it has 107 ratings. So my program is able to collect all of this data, and it nicely puts everything into a dictionary, which is then returned to the main script, and the contents of the dictionary are put into a Excel spreadsheet. Now that I had a list of professors with data from ratemyprofessors.com, I use this program here to collect data from critique.gatech.edu. Once again, I use Python's requests and beautiful soup packages to scrape the data from this website, and we were particularly interested in the average GPA for all of these professors, and as well as the average number of A's, B's, C's, D's, and F's. And this is what the website looks like, and you can see the data we're interested in is right here. And then the program returns all of this into an Excel file, which I will show right here. So as you can see, there's quite a lot of data from a lot of professors, and in total we found 1,400 professors that had data on both Rate My Professor and Course Critique. This data will later be used in our analysis section, which my teammates will now talk about.
After collecting all the data, we needed to clean it up. So I used this program called OpenRefine, which allows us to easily manipulate the tables. So for example, we can easily delete rows, delete columns, split columns based on their values. So here's what the initial data looked like in OpenRefine, and we can see that there are a lot of NA entries in the columns and rows. So we need to get rid of those, and we also need to split up the comments column which lists out all the different attributes that each professor can have. I removed all the rows with those NA entries, and now there are also a lot of columns that correspond to the different attributes a professor can have. There are around 20 total, and each professor could have 5 attributes. So there'd be a 1 if the professor had that attribute, and it'd be a 0 if they did not. So in the code to do the linear regression, where I was trying to predict GPA based on some features, I used scikit-learn's linear regression package and their polyfit for higher order polynomial fitting. So I did 4 different regressions to see which one would get the best predictive model. The first one was one feature with the overall rating versus GPA. Second was one feature with difficulty versus GPA. The third was 3 features of overall rating, difficulty, and the would take again, which is just the percentage of people that would take that professor's course again. And then 4 with those 3 features plus all of the professor attributes plus PCA dimension reduction. So the metrics of accuracy to see if this fitting was good was the self-written accuracy function, where I'm just seeing if each data point correctly predicts the GPA versus the actual GPA. And those prediction I did a little plus minus constant because there was a lot of variation in the data and the accuracy would be really low if I didn't do that plus minus. And I also used scikit-learn's training score and root mean squared error to see the fitting's accuracy. With the one feature overall rating, here are the results. So basically, I did 1 degree, 2 degree, 4 degree, 8 degree, and 10 degree while measuring the training accuracy, test accuracy, training score, test score, training mean squared error, and the test mean squared error. So looking at these, it looks like 2 degree has the best test accuracy, but not by much. And it's important to note that I had to write the accuracy with a plus or minus 0.4 in the GPA for calculating the accuracy, which is really large, and later on I'll explain why. Here's the data plotted with the 1 degree fit. So we can see that there's a huge variance based on GPA for each overall rating, and I think that contributes a lot to why, to make the accuracy somewhat relevant, we needed to add a plus or minus 0.4 in the GPA. We can also see a huge outlier in the bottom, so this data leads to this problem. So looking at the results for the one feature with the difficulty, it actually appears that the 8 degree appears to have the best test accuracy. And once again, we still had to write a plus or minus 0.4 for the accuracy function in the GPA. Here's what the GPA versus difficulty data looks like with the 1 degree fit plotted. And we can see it once again, there's still a lot of variance, though it's a little better. With the 3 feature results, some observations are that the training versus the test set accuracies follow a much more usual pattern. So for example, the test mean squared error actually increases pretty exponentially. And for this, also 2 degree is found to have the highest test accuracy score and the lowest mean squared test error. In the many feature PCA fit, we once again found that 2 degree has the highest test accuracy and score. So overall, with the linear regression, we found that the best model based purely on the highest test accuracy is the one feature with the overall rating. And it's important to note that with the large variance in GPA at each rating / difficulty and in the other attributes, we need to increase this huge 0.4 GPA buffer when calculating for prediction accuracy. So in the end, our model could get accuracy. It needed this buffer, so that's important to note.
Going into our classifier, we use the scikit-learn categorical naive Bayes classifier, and we basically went in and set a threshold on what is considered to be a good GPA and what isn't a good GPA. So anything above or equal to 3.25 would be considered a good GPA, and anything below that would be a bad GPA. So our model is trying to classify whether a professor gives a good GPA or not based on certain tags that students give them and ratemyprofessors.com. And so we use scikit-learn train test split to split the data between training and testing, and we use 70% of the data as training data and 30% of our data that was split into the testing data. We also use scikit-learn's metric package to evaluate our accuracy score as well as the precision and recall score of our model. And in the end, we use matplotlib to plot out our visualizations and evaluate our model. So this slide is a screenshot of the training data, and the first column we're using is the professor's name as well as GPA 1 or 0. If it's 1, that means that the professor gives a GPA of 3.25 or higher. If it's a 0, it means that the professor gives GPA below 3.25. And then some of our features that we're using is, for example, everything starting from inspiration to after. And if it's 0, that means that the professor does not have that tag on. But if it's a 1, that means that the professor was given that tag. So after training and testing our model, we achieved the accuracy score of around 0.74 and an average precision recall score of around 0.8. And then next slide, we'll discuss what that means.
So precision recall curve is a good way to evaluate the accuracy of a classifier, and it's especially useful when the class data you're using to build your classifier is uneven. So in our case, we had a lot more professors where they were labeled as having a good GPA rather than having a bad GPA, which is why we decided to use this plot. So basically, precision is the positive predictive value on the y-axis, and recall is defined as the true positive rate. And if you take a look at our average precision value, it's 0.74, which is pretty high. Here's an example of how our classifier would work. So if we had a professor's Rate My Professor up and we saw the tags that students gave them, but we didn't have their GPA data, then we could use our classifier to determine whether they would have a good GPA or not. So if this professor had so many papers, caring, graded by a few things, test heavy, and gives good feedback as attributes listed on the Rate My Professor, then our classifier would give us a value of 1, which means that they are classified as having a good GPA. One flaw of any naive-based classifier is the assumption of conditional independence of the features being used. And in our classifier, another flaw was that if a professor didn't have a tag listed for them, so for example, if caring were not a tag listed for a professor on the Rate My Professor page, we would just assume that it was a false value for our feature. And another flaw in our model was we arbitrarily determined the cutoff for a good GPA. So this could be changed depending on who's looking at the data and how it's being interpreted. And we defined this as having a good GPA is 3.25 or over. And we also felt that more data could have improved the accuracy of the model as well.
We first attempted to build several linear regression models to predict a professor's rating based on different data sets and attributes. We found that there were no large differences between the models based on overall rating, difficulty, or a combination of those and professor attributes. We also found that because there was such a large variance in the data as portrayed by these graphs, to achieve a reasonable level of accuracy in our custom accuracy function, we needed to add a buffer of 0.4 to the GPA. So in reality, the linear regression model may have trouble predicting a professor's GPA to a high degree of accuracy based on some input. We also built a naive-based classifier which took in professors' attributes from Rate My Professor and classified these corresponding professors as having good or bad GPAs, so that students could be informed on whether or not to take these professors. The classifier had an accuracy of approximately 74%. It also had a good precision recall score of approximately 80%. A user can input certain tags that may describe a professor, and the classifier will use these tags as features to determine whether or not that professor has a good GPA. Thus, this classifier is informing the student on whether or not he or she should take this class.